Hey guys, we're going to be talking about hybridization today. This video is going to be following up the Vesper and molecular geometry video that I posted recently. So we're going to get right into it here and talk about what hybridization is. So we talked about Lewis structures, we've talked about Vesper theory and molecular geometry, how those electrons cause the change and the shifting of the bond angles in the different geometries. And so today we're going to be talking about what hybridization is. So hybridization is a modification of Lewis structures, which is talking about localized electrons. That's where we drew our dots around the atoms. And so it's a modification of the localized electron model structure to account for the observations that atoms seem to use special atomic orbitals in forming molecules. So there are different types of hybridization. There are sp, sp2, sp3, d, sp3, D2, sp3. And so we're going to be looking at just a short bit of these. We won't be looking at all of these. And so we're going to start off with just sp3, and we're going to look at what sp3 hybridized means. So there are a couple rules that you have to follow in determining the hybridization. So the first rule is that you must draw the Lewis structure The second rule is you need to determine the arrangement of the electrons. And so really what that's telling you to do is look at Vesper and determine the domain that the atom is found in. We're talking about the central atom here. And then the third thing will be to use this information to determine the hybridization. So when we talk about sp3, sp3 means that you're going to have one s orbital and three p orbitals overlapping each other. So when we go back to quantum mechanics, we talked about s orbitals, p orbitals, d and f orbitals. In this case, this really reflects back to your quantum mechanics. And what this is discussing is trying to describe to you how the orbitals overlap each other. When we talked about Lewis structures, and specifically we talked about the sharing of the electrons. In this case here, this is trying to illustrate how the electrons in those specific orbitals overlap each other. So when we talk about sp3, we're going to have one s orbital and three p orbitals. So the best thing to do is look at an example. So let's take CH4 and let's break that down. All right. The first thing we're going to do is draw its Lewis structure, and its Lewis structure is found to look like this. The carbon itself has 4 domains, so it's tetrahedral geometry. Now, so 4 domains, tetrahedral. So now we're going to look at both the carbon and the hydrogen, and we're going to look at how their electron and their orbitals exist within the S shell and the P shells. So for the hydrogen, it's pretty simple. Hydrogen only has one electron, and that fills in the 1s shell. So it would just look like this. And carbon, on the other hand, has a 2s and 2p. Now I'm only focusing on the valence electrons. Remember, the Lewis structures are drawn just based around how many valence electrons there are. So we don't look at the core electrons. We focus only on the valence electrons. Carbon has 4 valence electrons. So we'd have 1, 2, 3, 4. Now, when you look at this carbon atom, you can see that it has an empty spot here and then 2 more spots. But we wouldn't put anything here because there's nothing here. Remember, electrons have to work in pairs. So really, if you focused on just the way we've drawn this configuration, really we only have 2 spots for the bonding to take place. Now, we see in the Lewis structure we drill that there are actually 4 bonds. So what has to happen here is that this has to hybridize. And so when it hybridizes, what happens is it opens up room for another 2 bonds to form. So when you look at it now what's happened here is that this electron here is hybridized, so it's shifted over into this 3rd p orbital. And so now when you bond your hydrogens, those are going to overlap with the S. So here's where you get your S, and then you've got 3 of the P's. So that's where that hybridization comes from, it's the sp3. So when we talk about hybridization, it's not that we are adding or taking away, it's just what happens is the electrons manipulate this, they rearrange themselves, they hybridize, so that way they can accompany the number of electrons they need to have in order to meet that octet. So that's one example. Another example that we can look at is ammonium. So ammonium is NH4 plus 1. So we're going to look at the nitrogen, and we're also going to look at the hydrogen. Before we do that, let's draw the Lewis structure. Alright, we see that the nitrogen has a plus 1 charge, and the hydrogens are covalently bonded, so there's 4 hydrogens. So you have, so there's 4 domains, so this is tetrahedral domain again, just like we saw in CH4. So the nitrogen has 1, 2, 3, 4 because it's lost 1, and then the hydrogen still has 1. So this one's very similar to what we just saw with carbon. The nitrogen is going to have to hybridize so that way it can accommodate the 4 bonds that it's going to have in between each hydrogen. So the configuration here is giving us an sp3 hybridization. So when we talk about sp3 hybridization, this is how we are able to obtain the sp3 hybridization. So the next hybridization we're going to look at is sp2 hybridization. So sp2 hybridization has 1 s orbital and 2 p orbitals. All right, just like you see it there, sp2. Now, so what's different here compared to what we just saw is that the double bonds oftentimes will form in an sp2 configuration. And so we look at a formula, C2H4. So this will be our example here. Now C, all right, there's 2 of them. So you're going to have your carbons, and so in this example here, there's 2 hydrogens on each side, so you're going to have a double bond in between the 2 carbons. So this would be the Lewis structure for it. Now, when you look at this Lewis structure, you can look at 1 carbon because the other carbon's a mirror image of that carbon. So what has to happen here is now if we draw out our configuration, we have this configuration normally, the hydrogen doesn't change, but when the carbon hybridizes, what happens here is that you end up forming this third. So if you look at what I've done here, this third orbital actually is a little bit higher in energy. So you still have your S and your P. What happens here now is that you're going to have this new configuration for the carbon. So it's not that we're doing anything really different. It's just we have to understand that this orbital up here, this electron, is actually found in a pi bond configuration. So that leads me to starting the discussion about sigma bonds and pi bonds. Sigma bonds are typically found in between the two nuclei, the two atoms. The pi bonds are found up on top and bottom and front to back. They're actually found outside from the nucleus because pi bonds are always higher in energy than your sigma bonds are. So when we go back and we look at this molecule's Lewis structure, if we were to talk about drawing and showing the orbitals overlapping, I did not show that in the previous examples. I will show you for this one because that's important because of where the pi bonds are found. So when we talk about the sigma bonds, all right, so the sigma bonds are found in the sp2 configuration. So when we look at this carbon here, this carbon is going to have an overlapping this carbon here. So your electrons are found in between there where they've overlapped of the electron cloud. And then you're going to have your hydrogen found here, and then you're going to have your hydrogen found here. So, and then the other side is the same manner. Here's the difference though. The pi bonds, remember I told you the pi bonds are found in a higher energy level, so they're not going to be found in between the nuclei. So that when I say in between, this is like the center. The pi bonds are not found in the center. What they're going to be doing is they're going to be found above and below, above and below, and so it takes two halves to make a whole. So in this case here, this is like a half a pi bond, and this here is a half pi bond, and they work in pairs like that. So this would make your pi bond. But where we get our configuration here, our hybridization, is the fact that you have the sp2. So you have your sp2. So you have this triangle, almost like your configuration in the structure. But you also see the pi bonds. Now, not all sp2 is going to be related back to pi bonds. There are examples where we can have sp2 configuration in other elements. So we're looking at BF3 for an example here. All right, so boron, trifluoride. So fluorine, there's 3 fluorines surrounding it here, and each of those fluorines are single bonded to the boron. You can see that it has this triangle effect, so that would be like 3 domains, right? That's trigonoplanar. And the same thing for over here, this carbon here is trigonoplanar, so you get that triangle. So when we look at this configuration for the boron, all right, you're going to have your S and your P, so it's going to look like this to begin with, but it has to hybridize. So it hybridizes into this configuration here, where you have your sp2. So we would see some overlap here within the orbitals of the borons and fluorine. Now fluorine's configuration, there's 7 valence electrons. So there's not much you can do here because there's no way to hybridize it. So there's only one place for it to be bonding at, and that's why fluorine can only have one bond. It's always going to have an octet, and that's right there where I circled it in green. So these are just a couple examples where you have sp2 configuration. There's one more configuration hybridization we're going to talk about, and that is sp hybridization. And so sp just means that you have one s orbital and one p orbital. So just looking at a simple example here for SP hybridization, you're going to have BeF2, so beryllium fluoride. So the beryllium is, now if we draw the Lewis structure here, it looks like this. And in fact, this is a linear domain, linear geometry. It's two electron domains, 1, 2. So you have two domains here. And the configuration for this would be, well, I drew the hybridized form. So you have S, and you have your P. So if you hybridize this, you're going to have one S and one P here. So this is where the BE ends up becoming SP hybridized. So that's just a very simple structure. And you won't run into too many that are like that, but this is where we can deal with triple bonds and double bonds specifically. So CO2 is going to be another example we look at here. So CO2 has a Lewis structure that looks like this. Now this one's a little bit different from the one we talked about in the SP2 hybridized, where we had the double bond. This actually has two double bonds. So yes, the carbon is going to have your 2S and 2P, 1, 2, 1, 2. But the difference here is now, since there's two double bonds, what's going to happen is that the configuration will now look like this, where you're going to have a shift. So up here, you're going to have two pi bonds for the double bond that you see up here, and the hybridization will be SP hybridized. So let's look at how that might appear if we were to draw the overlapping just like we did with the CH4 and the, what was the other one that I did earlier? C2H4. So now we have oxygen on each side. So the first thing we're going to do is we're going to have your overlap in between here, and then you're going to have your overlap in between here. So you have your S and your P. When we do the pi bond, remember pi bonds are typically found where? Above and below and front to back. So in this, on the left side here, we're going to have our pi bond above and below. Now, to fit in the other pi bond, remember what electrons do best? They repel each other. And so to minimize that repulsion, what the pi bond will be doing on this side is it will go forward and backwards. Forward and backwards. And so here you have your other pi bond. And so what these pi bonds do is the blue pi bond makes your double bond for the left side. The red pi bond makes the double bond for the right hand side. So that's how they would be drawn. But really what you need to be able to do is not necessarily draw, but to be able to determine and distinguish the type of hybridization that you're going to see. So we could do another example here, and let's do C2H2. This will be our last example that we do for the hybridization, at least drawing these diagrams. So the carbon again, this one's going to have a triple bond in between the two carbons, and then you're going to have your hydrogen there on the outside. So when we look at the carbons here, it's going to have the same form as what we see up here. All right, that's not going to change. So, but what we want to see is how it adopts those pi bonds, because now we have a triple bond, whereas over here we have two double bonds. So how do we illustrate the triple bond? That's what I want to do here and show you. Now the orbitals do overlap with the carbon and hydrogen, and they overlap in between the carbon and carbon. So if you were to count the number of domains here, and we look specifically here, this molecule would have two domains for this carbon and two domains for that carbon. So that's still linear geometry in reference to what we saw in the other two examples. The other two are linear also. So the question now is, where do the pi bonds take place? Well, you see that there's a triple bond in between the two carbons here. So the first pi bond is going to be above and below, so that makes the double bond. And then the other, to make that triple bond, is going to be front to back. So that's where you get your triple bond. So you have your single, your double, and your triple here. So that's how you would represent a triple bond in reference to the way they would overlap each other. In this case, they don't overlap, they are extended outwards from the nucleus of the two atoms. Okay, so there's two other hybridizations we want to talk about, and this is going to be very quick. There's DsP3, and then there's D2sp3. All these are reflecting, and this is where you really get into the exceptions to the octet rule. You get into the transition metals. So we're not going to go into detail about how you determine these and how you draw the orbitals overlapping each other. But you can see here you have 1D, 1s, and 3p's here. You have 2Ds, 1s, and 3p's. So quick way of kind of establishing what hybridization you're going to have is by determining the number of electron domains, and that comes from the Lewis structure. And so we have 2, 3, 4, 5, and 6 domains. So the arrangement of these are the geometries, but we're not really focusing on it. We just need to make sure we're able to count the number of domains specifically, and then we can sort of get an idea of what the hybridization is without having to draw it out completely. So for hybridization, if you have 2 domains, that's SP. If you have 3 domains, that's SP2. If you have 4 domains, that's SP3. And if you see there's a pattern here, so 2 domains represents S and P only, 3 domains represents S and 2 P's, 4 domains represent S and 3 P's. Now we get into 5 and 6 domains, and so 5 represents D, sp3, and then 6 represents D2, sp3. So if you add the exponents up, this one adds up to 5, 1 plus 1 plus 3, then 6 would be 2 plus 1 plus 3. So once you figure out the number of domains, you can get an idea of the hybridization as we see in this chart here. All right, thanks. Next video will be molecular orbital theory.